Thank you. So I'm like to start by thanking the NIH, without who this research would not be possible. So I'm going to discuss what it's a mouthful. The title says there, multi-context graph neural networks for enhanced multivariate time series analysis in healthcare. All right. So this is the outline of the talk. So I'll start discussing very quickly what we mean by spatial learning and modeling with graph neural network. And then I'll give you two applications that we have developed. The first one is on seizure detection from EEG signals. And the software is called NeuroGNN. And the last one is something that we're working on that is an extension of NeuroGNN to irregular time series, such as EHR data. So why is that interesting to look at spatial learning modeling with GNN? So it turns out that predicting health outcomes require to use a time series. These time series are available through different means, for instance, wearable data. And they are usually a large amount of data that you have to go and process. There is obviously scarcity of label data because you need some human to go and do that work. And therefore, our approach is to alleviate the problems that come with this type of data. Typically, wearable time series data are noisy and incomplete by adding knowledge and information. And as you would see, the dynamic graph neural networks are able to learn how health time series correlate between them and provide you with forecasts that are doing much better than what is the state of the art today. So to give you an example of what we mean by correlations in the time series, if you consider highway traffic sensors, you might have a sensor that is on the opposite directions of the highway that is correlated with the sensor on the current lane. So you want to capture those correlations, and those correlations can depend on time. So they can be dynamic, and you might not be able to know them in advance. Typically, on the highway system, when there is an accident, that impacts how the time series are going to behave and how the correlations are going to change. So this is very similar to what happens in the case of EEG signals and wearables in general when you have multiple time series that you're trying to process. So the main contribution of the work here is about learning the graph dynamically on the fly and integrated in the domain-specific context information that allows you to make the predictions. So NeuroGNN looks at the problem of forecasting and classifying seizures. So this is usually sourced from sensors that are placed on the scalp that are called leads that generate time signals. You see an example in the graph on the right side. So those we call multivariate time series, and usually experts are looking at those to try to classify and detect the seizures so that they can provide information that is used in treatment and management of the epilepsy. So this is obviously time consuming because people tend to look at large amounts of data for a given subject. Therefore, we developed this NeuroGNN that provides seizure detection and classification on EEG data. So this is a dynamic graph neural network architecture trained on labeled EEG recordings. And what it does is that it analyzes segments of data to detect and classify seizures by incorporating what we call multi-context correlation. So these are additional information that we're adding. So we got prompted to look into this from work that we've seen from a Stanford group that applied work that we have previously published in 2018 for doing the same thing to the seizure detection and classification. The slide here summarizes what we mean by multi-context correlation. So here we look at correlation in different domains, such as the spatial context, semantical, taxonomic, and temporal. So each one of these are going to enrich the model, and you will be able to understand different aspects of the modalities over time. The research was published recently, and it has already received quite a bit of press coverage. Here you see some of that. And I'll very quickly give you an outline of what we're working on now. So all the previous approaches work quite well on a regular time series. And now we're looking at the problem of integrating time series with other data that are usually have on subjects and that are typically irregular. So those can include blood pressure measurement, oximeter, temperature, and or notes that the physician takes. That happens at different times, and reconciliating that type of data and using it in an graph model together with the time series is challenging. So for that, we have an approach here, and the first results are very promising, and we hope to publish that in the coming months. Thank you.
I actually don't have a question, but I wanted to thank you to covering the multimodal aspect of it, and having was a great presentation. I appreciate that.
Thank you.
Question? Yeah. So could the approach be used as a warning to people suffering from epilepsy, for instance?
Yes.
For example, they can't go on a ladder, they can't drive, just for them to stop the activity they are doing.
Yes, part of the model is to do prediction. So you would be able, from historical data up to the current time, to predict and forecast future events. And in that case, you would be able to act and make the circumstances, I guess, more secure for people who suffer from epilepsy. We didn't try to do that, the real-time scenario, because we've been testing on data sets that are already created with historical data. But yes.